Welcome to our lesson on carrying capacity, the next in our series on populations. So, what is carrying capacity? By the way, I want to make sure to point out that carrying capacity, for reasons that are weird, is abbreviated as K. This is because it originally comes from a term that was in German, and in German, they don't tend to use C's a lot at the beginning of words, and it starts with a K. Carrying capacity is the maximum population size that a habitat can support. This depends on a lot of different things, including food, availability, habitat availability, water, and other resources. This is usually reached when a population is at equilibrium. By the way, equilibrium in any term in science usually means equal conditions. Sometimes this is on multiple sides of things. In this case, it means that the number of births in a population is equal to the number of deaths. So for every organism being born into the population, on average, one is going to die. And this can change when the environment changes. So a lot of times carrying capacity is represented as a bucket, and water is filling this bucket. The water represents the population. So the more water you have filling the bucket, the greater the population. There are some things that can decrease the population. So you have all of these events, like you can have human activities, you can have weather or other extreme events, diseases and parasites, losing habitat, predators and hunting, starvation and accidents. And then you have something that is increasing the population or adding to the bucket, which is the annual reproduction. And so your carrying capacity is the point at which the amount of population that's going in, or in this case, the amount of water that's going in, equals the amount that's leaving. So it's kind of like your limit in an environment for the population. This is a typical graph that you'll see of a population. And a lot of times, if you see one of these, you'll see a dashed line, and that is representing the carrying capacity. It's in some situations, if you have a graph that's showing this kind of idealistic growth, it may approach the carrying capacity and not quite reach it, but that's not realistically what we see in nature. In nature, you're going to see something called an overshoot where the population grows above the carrying capacity, and when it exceeds the carrying capacity, you have some organisms start to die, death rate increases, and the population decreases until you get below the carrying capacity where you have more resources, and then you're going to have your population rate start to grow again. And so, what you don't see is you don't see this kind of very steady sort of curve like with this ideal logistic curve. Instead, you see this kind of I call it yo-yoing around the carrying capacity, where you basically fluctuate around it. And if you don't know that word, it's a good one to know. It has shown up on the AP test before. Fluctuate means to go up and down. And so a lot of times the population of a species will fluctuate or go up and down around the carrying capacity. So we talked about overshoot really quickly, or at least it was pointed out on the previous graph. This is what happens when the population goes above the carrying capacity. Some of the environmental impacts of this, because you have a slight bit of overpopulation, at least for a short period of time, is that you can deplete resources. And then because you don't have these resources, that can cause things like famine, disease, conflict, especially if you're talking about human populations. And all of those things tend to decrease the population. Another way to look at it is these things also increase the death rate. So instead of the birth rate and the death rate being equal, now your death rate is higher, and that causes an overshoot. After an overshoot, which by the way here is highlighted in yellow on this graph, you will have a dieback, sometimes called a population crash. And what happens is you have this sharp reduction in population size. This can be anywhere from severe, meaning a large part of the population dies off, to catastrophic, where it can reduce a species to either extinction or near extinction in an area. And then this is, sorry, that's a repeat of the previous slide. Like I said, it's going to leading to famine, disease, and conflict. And that is this section of the graph right here, the dieback. So there are two different major types of population growth that I want to make sure that you are familiar with. Exponential growth happens when a population is growing at a rate faster and faster and faster, and it doesn't have a limit. Logistic growth happens when population is limited by some sort of factor. Usually this is, We're going to talk about this in just a moment, but density dependent limiting factors. And here are some graphs. These are common graphs that you may also run into something similar on the AP test. Exponential growth is only limited by the biotic potential, and it is something you will often see when a species colonizes a new area. And it's also very common with our strategists to see that, our selected species. Logistic growth, this is limited by environmental factors. This is more realistic. This is what you see in nature because we don't have unlimited resources for any species out there. Eventually, you're going to hit a limit. And it's limited by the environment, but it's also limited by the carrying capacity, which is a measure of how much the environment can support. So you're going to have at the beginning a period of exponential growth. But then the growth rate is going to slow as resources become more limited. And those are factors to keep in mind. Even in our strategist, while it may experience exponential growth in the beginning, eventually it will hit a limit and its growth rate will start to slow down and it will reach its carrying capacity. So exponential growth is something you only see in nature, if there is a new niche being exploited, or you have a species being invasive and moving into a new ecosystem, or you have a species just migrating into a new area. So, what are the factors that can impact the carrying capacity in the population? Well, these are known as population control factors, and there are two of them. There are density independent limiting factors that don't have anything to do with the population density, and there are density dependent limiting factors that are going to start to have more and more of an impact as the population density increases. By the way, in case you haven't come across this, density is the population per area. If you think about it, New York City, for example, would have a very high density of humans, but Wyoming as a state has a very low density of humans, very few humans packed into an area. So let's talk about density dependent limiting factors first. So high population densities tend to compete for resources a little more strongly. They tend to be more easily located by predators and parasites. They're more vulnerable to infection and disease, which is going to spread more easily in a crowded population. That would be why, for example, with the COVID pandemic, countries or areas with a high population tended to see a very quick spread of the disease, whereas areas that were more rural and more spread out saw a slower spread of the disease. This is a lot of times due to more biotic factors, so you can link those two things such as food supply, disease, parasites, competition, and predation, which are all density dependent factors. Density independent factors, on the other hand, tend to be more either abiotic factors or some sort of catastrophic event. So, some of the abiotic factors that can limit the population in an area are just the general temperature, precipitation, humidity, acidity, salinity. Some catastrophic events can limit the population as well, things like flooding, tsunamis, fire, drought, earthquakes, and eruptions. I said earlier that carrying capacity can change. I wanted to point out that if you have a population overshoot and it basically decreases a resource beyond the which it can recover, that can cause degradation of the carrying capacity, which is going to decrease or break down the carrying capacity so that it's lower. So here we see a graph of this is more of an economics thing, but it says consumption. We can replace that with population over time. And as you increase your population and you overshoot the carrying capacity, if you get a high enough population that it completely decreases some resource beyond which it can recover, that can degrade the carrying capacity. If you're wondering what's an example of this, well, in the early 1900s, reindeer were introduced to several islands off the coast of Alaska. But these islands were pretty small, and it turns out that the reindeer population increased so dramatically that eventually, so here we see an example on I believe this was St. Edward's Island. Notice the population reached about 2,000, and then after that, you have a population dieback or a population crash because the reindeer overgrazed the vegetation. Vegetation and plants grow very slowly in these cold environments like the tundra. And so, if you say eat all the moss and the lichen, it's not going to be able to reproduce or grow quick enough to get back to its previous level. And so, eventually, the plants died, the reindeer lost their food source, and then they died out. And most of these populations just completely died out. All right, that is the end. We'll start talking a little bit more about human populations soon in case you're getting bored with the organisms that are not human.